Hello all, welcome back to the last part or the final part of lecture 9. In this video we will be doing some hands-on on how to do bootstrap regression for capital asset pricing model. So here in our this piece of code you have already seen. I'll quickly remind you that we are going to use a T-series package. Then we are going to use system date or start date. Here we are. Then now this piece of code, line 6, 7, 8, is going to download the data from internet, from Yahoo Finance. So here we have data is downloaded from Yahoo Finance and rel. So here you can see. Then Nifty 50 data will be downloaded just at close prices as of 8th February 2023. All the data has come. Then we are going to merge these data. Here in line 13 we are going to calculate the log return. Here is the log returns in percentage term. So let me increase the font size a bit. Maybe I will use 24. Apply. Okay. All right. And now I'm using risk-free rate 6%, annualized 6%. So I'm dividing it by 365. So this is the daily risk-free rate. Then I'm subtracting risk-free rate from the return, log return. So calculating risk premium and then drawing the plots of risk premium. Grids are being drawn, and then here are some AB lines, and then so the fitted line. This is the fitted line using OLS method. So here I'm fitting CAPM using OLS method, and here is the summary statistics. So okay, so one possible problem is if we make the font size too big, then it will not come as nicely as we would like to see it. So now it comes a bit nicely. And then we can take the residuals and then plot the residuals, and then can do the Bartlett's rank test, and then we did Brugsch-Pagan test, rank test and Brugsch-Pagan test. Everything was quite good. Then when we did a test for normality, it was kind of get rejected, and that's where the whole problem starts. So we decided to do a bootstrap regression. First we are going to apply paired resampling method or paired bootstrap regression method. So here we are assuming risk premium equal to A plus alpha plus beta, A plus B times market premium plus error. And we are assuming this idiosyncratic return or E is following some distribution. We don't know what is that distribution. Some distribution F with expected value of E to be 0 and variance of E to be sigma square. But we don't know what is that distribution is. This could be any distribution. So we put it as a data frame. Here is the number of samples is 62. We have taken bootstrap simulation size to be 1000. You can increase it to any number, 10,000 or anything. And then I am defining a beta star, a matrix of sample simulation size n, and number of columns is beta 2, because I'm going to estimate alpha and beta. So sorry, I have to run this. Okay, now if you see, I've created this matrix with column name alpha beta, and it has size of, it has basically if you just go up about 1000 rows number of simulation. Now I'm going to also create another place for R square. I'm calling it R square star. Then here my loop start, bootstrap regression, bootstrap simulation starts, bootstrap simulation starts. So first from 1 each to n id, I'm going to draw randoms id. I'm going to draw the random IDs, and those IDs I'm going to take the samples, random samples from the samples itself. So RT1 is the sample itself. From there I'm going to draw random samples, and those are, that is the RT star, and from the RT star I'm going to, you know, fit the model, and from the model I'm going to calculate the summary, and from the summary I'm extracting the coefficients alpha beta, okay, and the adjusted R square. I'm keeping it here. So let me just run this piece of code, and it's run in almost no time. And then I'm going to summarize the bootstrap statistics here. So if you, and then estimate standard error and 25%. So now if you run this, so estimates are like negative 0.0012 and 0.12. So now you can see the alpha is containing the 0, the confidence interval. This is the confidence interval for alpha, and it contains 0. And similarly, this is the confidence interval for beta, it contains 1. This is for reliance. And remember that summary statistics for CAPM, this is the OLS thing. So if you now carefully look into it, that OLS estimate is 0.0013, and if you round it off to 4 decimal places, it is actually negative 0.0013. Beta is 1.1307. This is beta here 1.12327. This is the coefficient. So now, since the underlying distribution does not, or underlying model assumption does not hold good, so this inference based on t value and p value is not valid inference. But here I'm assuming that the underlying distribution is just unknown, and I'm doing a non-parametric test. So this inference is valid, though there is not much change in my inference, but this inference is valid. Here the adjusted R square is given 0.467, but what we can do is, essentially we can just say summary of this. So this is the bootstrap statistics for the R square, adjusted R square, and we can quantile, say we can create a quantile of R square with probability equal to 0.025, 0.975. Now this gives me a 95% confidence interval for adjusted R square. Now typically it's very difficult to get any statistical inference for R square, but using Bootstrap we can calculate a 95% confidence interval for adjusted R square. So this is a very interesting thing. So you can, here we have the alpha, the sampling, this is Bootstrap sampling distribution of alpha, and here is the density that we are drawing. And then if you would have lines, and similarly we can do the histogram of the, this is the beta and this is the lines. If we do the beta star, this is the distribution between, joint distribution of, sampling distribution of alpha and beta, and we see that there is not much correlation that we are seeing between alpha and beta, which is a good actually. So here is the sampling distribution of bootstrap sampling distribution of R square. Here is the lines density, kernel density. Here is the R square. Now we are going to do the residual resampling or residual bootstrap regression. Okay, and from the CAPM we just take the OLS and OLS residual and OLS predicted values, and then this is the adjusted nifty, and same way we define the matrices. Now here we are starting the bootstrap statistic, bootstrap simulation, bootstrap simulation. Now here is the ID star. I am from the OLS residual, I am just simulating the residuals. Then from the predicted OLS predicted value, you just take the predicted star, predicted value, because X beta hat is nothing but the OLS predicted value, right? And then you just add the error, and that will give you the Y star. And then based on the Y star, you compute the again fitted value and CAPM star, and then all you do from there you compute the coefficients, and from the coefficient adjusted R square. So same way you just do that. It's very fast. For 1000 simulation it does very quickly actually. So here is the estimates. The estimates are pretty much very close to similar previously, and confidence interval also doesn't change much. So residual bootstrap holds pretty much similar, not much change, because, and this is the alpha distribution of alpha, this is the distribution of beta, this is the joint distribution of alpha and beta when we are doing residual bootstrap regression. So that's how we do paired bootstrap statistics or bootstrap regression and residual bootstrap regression. If sometimes what happens, as you know, that you fit the model, and what happens is you fit a model, you did a very good job with modeling and do a reasonable prediction also. Suppose you have achieved a decent R squared, very reasonably low RMSE, but and most likely you are okay to accept the model to the production. Now people can still raise question that if the model assumption doesn't hold good. Now oftentimes what I have seen that if the case is that randomness is okay and homoscedasticity is okay, then it is the distribution that is the problem, because distribution is always a very strong assumption. Then I will always recommend you to resort to bootstrap. So if you do the bootstrapping, what happens is you still work with the same model, only the statistical testing of hypothesis and the inferences now you are doing with the bootstrap distribution instead of assuming residual is normal. But rest of the assumptions is perfectly fine, and if even the homoscedasticity doesn't hold good, you can still work with paired bootstrap statistics and it will still work. So bootstrap regression is a big help for the statistician in case you have to do a statistical inference. That particularly if the model prediction is good. If the model prediction is not good, then of course you have to figure out a better model in that case. But if the model prediction is good, if the model is doing reasonable prediction in the out of the sample, If the model is doing, if the RMSE pretty low, if the R square, adjusted R square is reasonably acceptable range for given domain, then just for inference, you may find that the normality assumption is too strong assumption. In that case, you can do a statistical inference using Bootstrap statistics, and still you can go on with that prediction of the model or that predictive model, because that predictive model do reason if it does good with good prediction, then inference can be done using Bootstrap sampling distribution. So you will be good in that sense. So you can salvage that situation when the model check assumption is not holding good, as long as the IID sample assumption is working fine. You can salvage that situation using simple Bootstrap statistic technique. So with that, I will stop here for this lecture and looking forward to the next lecture. I hope you enjoy this hands-on session. It's a very useful. I find it in my many real-life project. I find it very useful, this technique. So I hope you will enjoy it and you will be able to use it and for your project experience. So thank you very much, and see you in the next topic and next video, next lecture.